Hello and welcome to the Drexel Interview. I'm your host, Paula Morantz-Cohen, speaking to you from the Leonard Pearlstein Gallery of the Antoinette Westphal College of Media Arts and Design at Drexel University. Today my guest is the astrophysicist Max Tegmark. Dr. Tegmark came to America from Sweden in 1990 to pursue a PhD from the University of California at Berkeley. Following posts at Princeton and the University of Pennsylvania, he is now a professor of physics at MIT. He's the author of numerous books and papers and has a reputation for original, often controversial views about the nature of the cosmos. His most recent book is titled Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. Dr. Tegmark, welcome to the Drexel Interview.
Thank you so much. It's a real pleasure to be here. But just call me Max, okay?
Max,
Because I hate formalities.
All right. Well, this book that you wrote, Our Mathematical Universe, is a kind of memoir, a memoir of your life in science. And I wonder, at this relatively young age that you seem to be, what prompted you to write a memoir?
Well, that's a good question, because this book, but even though this book is much more about our universe than it is about me, I decided I wanted to include some personal elements in there. And my reason for this was not because I felt a great need to talk about myself, but rather because I wanted to share with people not merely a bunch of facts about how amazing our universe is, but I wanted to also share with them how exciting it is to get to be part of this quest to try to understand our world better. I feel so fortunate myself to have gotten to contribute in a small way to this quest, and I feel it's in a way the greatest intellectual adventure of all times. So I want the reader who decides to read this to feel that this isn't just my quest, but our quest. And
well, you managed to do this. I have to say, it's a very compelling narrative.
Thank you.
What I found also interesting is that the way in which you came to physics. You say that you were not initially taken with physics in high school. That you you thought you would go into economics. Obviously, you were very strong in mathematics, and you thought you would bring that ability to bear on economics originally. And then you read a book by Richard Feynman, the great late physicist, and that seemed to have changed your mind. Could you tell us what it was about that book that inspired you?
Yeah, physics was honestly my most boring subject in high school, and Richard Feynman managed to have this huge impact on me, even though I never had the fortune to ever meet him. A friend of mine gave me this book and said, hey, check this out, it's a cool book. It wasn't about physics at all. It was about picking locks and his various intellectual adventures, but I could tell between the lines that he just loved physics. So I started reading a physics book by Feynman, and it was an epiphany. This light bulb just went off in my head, and I realized that physics is not just some boring cookbook recipe for calculating stuff. It's a detective mystery. It's the greatest mystery of all time, to try to understand how our world works.
Well, I have to say that you transmit that fascination in the book. It is really compelling, and it's also very lucid. It's very clear. I mean, as clear as something this complex can be. But one thing that struck me, as that you explained extremely well, was this idea of inflation, of the fact that the universe, our universe, is inflating. And it seems that that idea has very important connections to the idea of the Big Bang, or perhaps multiple Big Bangs. I wonder, can you, I know it's a hard thing to do in the short time we have, but can you explain succinctly for us this idea of inflation and how it connects to the Big Bang?
Yeah, absolutely. So when I first started studying physics, the standard story that we were generally told was that once upon a time there was this Big Bang, and it just happened. And you shouldn't ask why. That's just the way it was, And there's something very unsatisfactory about being told that don't ask questions, because that's, to me, totally against the spirit of science, being asked that, no, this is off limits. If there's some kind of mechanism that creates Big Bangs, That would be more satisfactory. But whenever we humans have had come up with a mechanism for producing anything, if you have a machine that can produce bottles, for instance, you would expect it to be able to produce many bottles, not just one. So if there's a universe-creating mechanism that's out there somehow, why should it have only created this one? And then what happened was Alan Guth and colleagues of his came up with this remarkably beautiful and simple mechanism, which is known as inflation, which takes a subatomic speck of matter and just keeps doubling and doubling and doubling its size over and over again, which rapidly makes it vastly larger than everything we can see and call our universe. And it also makes it, of course, expand very fast because of all this doubling. And it effectively puts the bang into our Big Bang. It predicts successfully a whole lot of things which we have now measured with great precision, like this map here of our baby universe that was just released last year from a fantastic space telescope called Planck. So it's become the most popular explanation for what made our Big Bang, but generically it actually predicts that there were many Big Bangs, and this is just one of them. So it also gives us humans a little bit more humility. That's why our book here is not called The Mathematical Universe, it's called Our Mathematical Universe, because I feel it's arrogant to talk about the universe, since it sort of presupposes that ours is the only one.
You talked about the very large and the very small, and you actually have in your book a section called Zoom In and Zoom Out. And I think it's very intriguing for those of us who are not in physics to think about the idea that the very small and the very large come together in cosmology. That we have quantum physics on the one hand and cosmology on the other, and that they connect. Could you explain how the very small and the very large, the zooming in and zooming out, are connected?
Yeah, that's a fascinating realization I think we've come to gradually as a community. The two quests, the two intellectual journeys that this book first launches into is the outward one you mentioned, where we zoom out and ask how big is reality really, and then the second one where we ask what's everything made out of and go into the micro world. And it turns out that to figure out the ultimate building blocks of protons and quarks and et cetera, what you need to do is smash them together with enormous energy to try to break them into smaller pieces. And we humans build machines like the Large Hadron Collider at CERN, but our universe itself has already done this experiment much more violently in our Big Bang.
Yeah.
So the best place to learn about the smallest scales in the world is to actually look at the very biggest scales, at the evidence that came out of our Big Bang.
I'm fascinated by this idea of parallel universes or multiple universes or multi-universes. And you spend a lot of time in your book talking about them. Can you explain some of the varieties of multiple universes, or perhaps the general concept of the multiple universe to us?
We've again and again and again throughout the history of science realized that everything that we thought existed was just a small part of some grander structure. Our planet was part of a solar system. It's part of this grand galaxy, which is part of a cluster of galaxies, part of what we call our universe. And when we say our universe, we don't mean everything, all of space even. We simply mean that the spherical region of space, which is depicted here on the front of the book, from which light has had time to get here so far during the 13.8 billion years since our Big Bang. And that begs the question, if we talk about that as everything that exists, are we again making a mistake? Kind of like an ostrich with its head in the sand saying that everything we see is all that exists? Or could it be that space simply goes on farther than that? If it does, then there are probably more galaxies out there, and we might have to wait another 10 billion years for the light from them to reach us, but it would be very arrogant to say that they're not real.
Now, is this equivalent to, if you take the idea of infinity here into account, is this sort of like the monkey at the typewriter sort of idea?
Yes.
You know, that if you put a monkey at a typewriter for an infinite length of time, he will eventually write all of Shakespeare.
Exactly right. If there is really infinity, which is a big if, then this theory of inflation is the ultimate monkey at the typewriter, because it's going to create an infinite space. And we know that no matter how unlikely it is that you monkey around at the typewriter by putting atoms in random orders and end up making a planet where life evolves and learns to speak and think and ultimately have this conversation, we know that the probability for that is not zero, because here we are, it happened. So if you have infinitely many other typewriters, then many other universes, the probability is 100% that it's going to happen again somewhere else. And it gives this very bewildering idea that there are these alter egos of ours out there.
It seems to me that there's another facet, or perhaps another kind of multiverse that you describe in your book that has to do with the laws of physics, and that has to do with specifically the divergence between what I'm going to do and what one thing that I might do and something else that I might do. And I wonder if you could explain that. Am I getting this correct?
You are.
Yeah, okay.
Can we have a universe, please? So this is our universe, the region of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang, with our latest photos of the edge of it here. And it struck me once upon a time at a conference that people were talking about a lot of different things that they called parallel universes, even though they were actually totally different ideas. And that's when I came up with this classification of parallel universes into level 1, level 2, level 3, and level 4, so people could at least know what they were talking about. So far, we've spoken about level 1, which are simply other regions of the same space, this size, elsewhere. And now we're getting into the third level, which has to do with the fact that you and I and everything around us is made of these elementary particles, like quarks and electrons. And we've studied in the lab and discovered that they can actually be in multiple places at once. So if your particles are all both here and also there, then you should be able to be in two places at once. When you work out the math for this, it turns out that, yeah, this is not only possible, but there's an effect that censors you from ever knowing about this other version of you. You'll be unaware of it. The only manifestation of it that I talk about a lot in the book is that sometimes it feels like something happened at random. That's how it feels when you actually sort of split into two different parallel tracks in the level 3 multiverse. So for instance, if you're really trying to just make your mind up about whether you should try to run that light that's about to go red, or play it safe and step on the brake, your snap decision might come down to what ultimately just one particle was doing in the little synaptic junction in your brain. Because it could trigger a whole cascade of neuron firing, which could make ultimately all the difference. So if that particle is in two different places at once, in the end, you and your car might be in two different places at once. And one might have an accident, the other might not. And from there on, the two histories of the world could really branch apart.
But wouldn't this be the case for every single minute element of what one would do?
But the bottom line you're making here is very valid. If there are these parallel universes, we have to be open for the idea that they might not just be kind of big, but really huge. So a large variety of all the counterfactual histories that you could find in literature would actually exist for real out there somewhere, as long as they don't violate any of the basic laws of physics. It can be sort of bewildering, but at the same time, as thinking big has revealed that everything we thought existed was just part of something bigger. In other words, we've underestimated again and again the size of our physical world. I think there's another much more optimistic trend in parallel, where we can see again and again and again we humans have underestimated also the power of our human mind to understand the world around us and even shape it for the better. I think the ancients who walked around here on this planet 50,000 years ago and looked at the stars, they made up these beautiful myths for what was going on there. They were just as intelligent as us, but they probably felt a little bit sad and powerless, knowing that they would never be able to know for sure what those shining dots sparkling in the sky really were. And they underestimated themselves, right? By using not rocket power, but mental power and letting our minds fly. It's just incredible how much we humans have been able to figure out. And I think we shouldn't knock ourselves. I think it's so easy in this day and age to feel powerless. Well,
you're very optimistic. I have to say the whole book is driven by a kind of optimism that's wonderful to read. And yet, of course, the argument could be that where are we going with this knowledge? Are we eventually going to know everything? I mean, do you see that as a possibility, or is this an asymptotic knowledge, always something out of reach? I do agree that the more knowledge we have, the more perhaps positive influence we can have on our environment, on each other. But where, do you see a limit to this, or do you see this as an infinite, to use the term that we've already discussed?
This is where it gets really controversial.
Yeah.
The reason the word mathematical is in the book title here has to do with this. Some people think that it's sort of obvious from the get-go that we're doomed to ultimately hit a roadblock in our understanding beyond which we just can't proceed. That we will run out of mathematical regularities in nature that we can exploit to understand things better. I also explore the opposite extreme, the optimistic extreme here, that there actually is no roadblock, that ultimately everything in our world can be understood with elegant mathematical equations. And if I'm right, then that means that we can, in principle at least, understand everything. And our ability to comprehend the cosmos is really only going to be limited by our creativity and imagination. I think another lesson to take from this is that even though we're small physically, I feel we should not feel insignificant, because it's perfectly plausible that life is so rare that we are the only planet within this region here that we call our universe to have gotten to the point of inventing the telescope. And that means that when you look at a galaxy, which I think is sometimes beautiful enough that it can go in an art gallery like this, and you say, wow, the Andromeda galaxy is so gorgeous and so beautiful. Why is it beautiful? It's only beautiful because a conscious being experienced it. If there were no consciousness, if we weren't here in the cosmos, it would be a giant waste of space as far as I'm concerned. So rather than just looking to the universe to give meaning to us, I think we should be aware that we are giving meaning to our universe. Our universe has been here for 13.8 billion years, but the vast majority of these galaxies only became meaningful a few hundred years ago when we invented the telescope.
I am struck by the fact that you physicists share knowledge very readily. One thing that I have heard is that the physics community will post things on a regular basis and share. Do you think that there is an unusual sort of communitarian spirit among physicists? I also know that physicists have huge egos, which would seem to counterbalance that. Could you tell me a little bit about cooperation within the community and the possibility for global work across, distances and nations and so forth to make the next breakthrough happen?
I find the physics community to be a wonderfully idealistic community, very much like a community of artists. And this is another reason why I chose to throw in the occasional personal element of this, to convey that. Every single professor I know could make much more money if they chose to not work in academia. So that tells you that they're doing what they're doing not for money, but for love, for passion, because they are so curious about these things, and this is what they feel in their heart they want to do. And it's just such a treat for me, an honor to get to spend my time with people like that, who are doing something for the best of all reasons, because of their own passion. And this is a passion which completely transcends borders, as you mentioned, languages, political views. Even during the coldest parts of the Cold War, the one group that always managed to get along were the scientists. Mathematicians and physicists in the Soviet Union and the US would secretly keep in touch about their latest theories and so on. They respected each other. There was no in-group, out-group there. It was us scientists who were on this quest together to try to understand our universe a little bit better.
Besides Feynman, I guess Einstein as well, because you do mention him quite a bit in your book, are there any other heroes of yours or people, whether alive or dead, who you look to as models within your field?
There are, absolutely. One who was very influential for me was John Archibald Wheeler. He was the last titan, in a way, surviving, who had been working with Einstein and Bohr and so on. And when I first saw him at a physics conference once upon a time in Copenhagen. I was so nervous. I really had to work on myself to even work up the guts to go talk to him. But I did anyway, and I was just absolutely taken aback by how compassionate he was and how he treated me with such dignity that I didn't feel I deserved at all. I felt he basically, I learned to know him a lot later and noticed that he treated everybody with an equal dignity, regardless of their rank or what accomplishments they had. And he basically treated you like you really had something to add and contribute to this. I felt that he believed more in me, maybe, than I believed in myself.
Yeah, what a wonderful thing to have in a teacher.
Yeah.
You describe in your book a couple of occasions where you were very excited about a breakthrough idea that you had or thought you had, and then discovered that it had been discovered before.
Yes.
Could you address that a little bit?
Yeah, absolutely. I mean, it's first of all, when you rediscover something, of course, don't realize that until days later that you've been scooped. So it feels exactly as exciting as it does when you discover something and later realize that you were the first.
Yeah.
All this exhilaration and excitement you have is exactly identical, and it's one of the most exciting rewards you ever get as a scientist. Who cares about what other people think and so on? It's just like if you're an artist, if you manage to write a poem that you're just really, really inspired by, that in and of itself is a fantastic reward.
It's an interesting comparison, though, because of course you would never write a poem and then discover someone else had written the same poem.
That's
and I
true.
guess that is the difference between science and art. There's something provable at the end.
That's true.
And that it is original or it's not original. And I guess that that notion of being testable is what is at the heart of science. And I guess getting to your book and some of your ideas in your book, which are quite exciting, they have been critiqued by some people for not being testable. What do you say to that?
I say to them that, first of all, I think people who raise that critique usually have not read the book, because I talk at great length about how I feel it's extremely important that everything is testable. That's the ultimate dividing line between science and speculation. What we have to remember about these most controversial ideas about parallel universes is that parallel universes are not a theory. They are a prediction of certain theories, which in turn aren't often testable. For example, we have the theory of general relativity by Einstein, which is testable because it predicts all sorts of things about the motion of Mercury around the sun and the bending of light by stars and how the GPS in your cell phone works and stuff. So we take it seriously, and therefore we also take seriously things it predicts that we can never test, like what happens inside a black hole. If you don't like black holes, you can't just dismiss them and say, I'm going to opt out of the black holes because this is untestable. You have to then come up with a different mathematical theory that violates Einstein's theory, that can explain everything else, but doesn't have the black holes. And that's very hard. So the analogy here is we have the theory of inflation. It's the best theory we have for what put the bang into our Big Bang. It has passed a lot of tests already. It predicts parallel universes. Does that prove that the parallel universes exist? No, because we haven't proven inflation. We're going to make more tests. We might rule it out next year, in fact, with another new detailed experiment. But that proves that the inflation theory is a testable scientific theory, which in turn means we need to take seriously its consequences. And if we don't like the parallel universes, don't blame them. Blame inflation. Try to come up with a better theory than inflation. A lot of people are trying. But right now, most of my colleagues still put their money on inflation. Same deal with those quantum parallel universes that we talked about. Here, you have a beautiful, simple equation called the Schrödinger equation. If it applies to everything, then we're stuck with these parallel universes. How can we test? We can test by trying to build quantum computers, which exploit all this quantum crazy parallelism to be able to calculate things faster that an ordinary computer could never do. There's a huge effort around the world right now to try to build these machines. If it fails, because we realize that the Schrödinger equation actually isn't quite correct, then all these parallel universes are ruled out because we killed the theory.
So the theory,
so it's testable.
The theory is creates other theories that must follow from it. And once we discredit the theory, then we will throw out what would follow from it. But you're saying
Exactly.
these things have to follow from the theory if the theory is valid.
Exactly. And if you don't like the implications of a theory, then try to come up with a better theory. And people that doesn't have those implications, but that can still explain all the other wonderful things that quantum mechanics can explain, like why the transistor in your computer and your cell phone and your laser work. And people have tried now for about a century to come up with something really different from quantum mechanics, which violates the Schrödinger equation, and it hasn't really caught on well. It's proven very hard to come up with an elegant mathematical theory that explains everything that we've already measured and tested and predicts that there is nothing else that exists than just what we see.
Well, we are out of time, and I want to thank you for this really exciting conversation. I wish I could go on with you for another half hour.
We can in the parallel universe where this
we
is a
are
longer
doing
show.
it now as we speak. But it's been a pleasure. I want to thank you for being here today, Max Tegmark.
Thank you so much.
Thank you.
Thank you.
And thank you for joining us today at the Drexel interview.